So any macroscopic property which depends upon only initial and final state is a state function. Say for example, the internal energy. See, in when the system is in the state A, internal energy is UA. When the system is in the state B, the internal energy is UB. So when a system changes from the state A to state B, it performs a work. A work is done. And for that work, a heat energy Q is spent. I am supplying an amount of heat energy Q, and the system is doing a work W. So what will happen? What will happen? The delta U, that is the internal energy change. Delta U is UB minus UA. UB minus UA, which is actually equal to what is the heat content, heat energy you have supplied, and what is the amount of the work it is done by the system. So it is Q minus W. Q is the heat energy supplied, and W is the work done by the system. So what is remaining will be the rise or decrease in the internal energy. So in generalized form, I can write delta U is equal to Q plus W, which is called the mathematical statement of the first law of thermodynamics. So now what happens when the W is a work done by the surrounding on the system? See, compression. During compression, the work is done by the surrounding on the system. Then a sign of plus is given for the W. But when the work is done by the system on the surrounding, it is expansion. For expansion, the sign given for the W is minus. So accordingly, this equation will change. It will be delta U Q minus W or Q plus W, which depends upon what type of work is done. If the work is done by the surrounding on the system, it will be plus. If the work is done by the system on the surrounding, it will be minus. If the work is done by the system on the surrounding, it is minus. If it is by the surrounding on the system, it will be plus. So now look at this problem. You can understand any physical chemistry concepts when the problems, numerical problems, are worked out. Now you carefully read this problem. Calculate the work done and the internal energy change for the conversion of 1 mole of water at 100 degrees centigrade to steam at 1 atmospheric pressure, and the heat of vaporization of water at 100 degrees centigrade is 40,670 joule per mole. Look here, I am taking 1 mole of water. 1 mole means Avogadro number of water molecules. So 1 mole of water is taken, and I am heating that water at a temperature 100 degrees centigrade, and I am converting the water into steam, and I am maintaining the pressure 1 atmosphere. So the heat of vaporization means that is the heat energy spent for the vaporization of 1 mole of water is 40,670 joule. Now what is asked is the work done. First, you take 1 mole of water and it is converted into steam, and the Q, the energy spent, is 40,670 joule, and the pressure of the system is 1 atmosphere. Pressure of the system is 1 atmosphere. So volume, initial volume, that is 1 mole of water, the molar volume, this is what we call molar volume. If you take 1 mole of water, it will be 18 ml. See how I calculated this 18 ml, how I am able to get this 18 ml. You take 1 mole of water, the molecular weight of water is 18 gram. Actually, gram is not the unit of molecular weight. If you take 18 gram of water, it will contain 1 mole of water. So because atomic weight of oxygen is 16 and the hydrogen is approximately 1. So 2 hydrogen atoms, 1 oxygen atom. So 16 plus 2, it is 18. So if you take 18 gram of water molecule, it will contain 1 mole. Water, the density is 1 or specific gravity is 1, which means if you take 1 ml of water, it will weigh 1 gram. So what happens if you take 18 ml of water, it will weigh 18 gram. So which is converted into volume, it is 18 ml. So 18 gram water will be 18 ml. So that 18 ml is converted into SI unit, which is 18 into 10 power minus 6 meter cube. Now, what is the volume 2? There is a volume change because when the liquid water is converted into vapor water or steam, certainly there will be volume change and there will be increase in the volume because liquid water occupies a small space and the gaseous water, water in vapor state, it occupies more volume. So there is an increase in the volume. And actually, in the first class itself, or in the last, I think you might have studied this in the first year gaseous state. 1 mole of any gas will occupy a volume of 22 point liter in the normal temperature pressure condition. So at a normal temperature pressure condition, which means at 1 atmospheric pressure and 273 degrees centigrade, any gas of 1 mole will occupy a volume of 0.0224 meter cube. So from the ideal gas equation and other things, we have already known that P1 V1 by T1 is equal to P2 V2 by T2. So according to that equation, we have made this volume 2 is equal to 0.0224 into the temperature T2, the T1 273. So at 273 Kelvin, the volume of any gas of quantity 1 mole will be 0.0224 meter cube. So what will be its volume at 373 Kelvin, which is 100 degrees centigrade? So it will be 0.0306 meter cube. So what I am doing, I am just calculating the work done. Work done is P into delta V, the pressure into the change of volume. So P into delta V, that is P into V2 minus V1, which is equal to, what is P? Pressure. Pressure is 1 atmosphere. 1 atmosphere has to be converted into Newton per meter square. So pressure is the force acting per unit area. What is the force acting in unit area? That unit area is given in meter square in SI units. So 1 atmosphere is it is 101325 Newton per meter square. So that is substituted here. And then volume is V2 is the final volume, which is 0.0306 meter cube minus what is the volume 1, which is the molar volume, 18 into 10 power minus 6 meter cube. Actually, 18 into 10 power minus 6 means 0.0000. So what happens? You have to neglect this particular volume because the molar volume comparing the expanded volume of the steam, it is negligible. So this particular volume is neglected, and what you are ultimately getting is 3100 Newton meter. See, here it is a Newton per meter square, here it is meter cube. So Newton per meter square into meter cube will give you Newton meter. Newton meter is nothing but joule. So totally the work done is 3100 joule. Now the vaporization is expansion. So when the liquid is converted into gas, it is expansion. Expansion means the system is doing the work on the surrounding. The work is coming out. We have already discussed the sign of a W. When the work is done by the system on the surrounding, it will be negative. And when the work is done by the surrounding on the system, it will be positive. So here the work is done by the system on the surrounding. Therefore, the W is equal to minus 3100 joule. So in order to calculate the delta U, what is the Q supplied? It is Q is the heat energy supplied by us for the conversion of water into steam. It is 40,670 joule plus what is the work done? It is minus 3100 joule. So The subtraction, the remaining is 37,570 joule is the internal energy change. So this much of internal energy change is accompanied during the conversion of 1 mole of liquid water into gaseous water at 1 atmospheric pressure at 100 degrees centigrade. I think from this calculation, you might have clearly understood the first law of thermodynamics. Now look here, I want to discuss what are state functions. State functions are depending upon only the initial state and the final state. It is not depending upon the path in which the states are arrived. And there are other functions called path functions, which depend upon the path of a particular process. Look here, the state function is a pressure, temperature, volume, energy, internal energy. All these things are state functions. Path function, the energy supplied, the work done are path functions. So when you differentiate the state functions, what you are getting is the exact differential. When you differentiate the path functions, what you are getting is inexact differential. See, the simple understanding is this. Suppose I am differentiating the internal energy between the limits u1 and u2, the integral u1 u2 du will be equal to u2 minus u1. If you are getting this particular equation, then the differential is called exact differential. But such an expression cannot be made for q and w. See, integral q1 q2 dq is not equal to q2 minus q1. So this is not exact differential, this is inexact differential. Similarly, for work done also, integral w1 w2 dw is not equal to w2 minus w1. So the work done and the energy supplied are not exact differentials, they are inexact differentials. For the further clarification, in order to have a clear look at the exact differential and the inexact differential, you have to derive the Euler reciprocity. See, suppose Z is a function of x and y. You are partially differentiating the Z with respect to x and with respect to y. You look at this equation, the dz equal to dou z by dou x, which is, it is partially differentiated with respect to x at a constant y into dx plus dou z by dou y at a constant x and dy. Let me say this is m of x, this is n of xy. So I can write m of xy into dx, n of xy into dy. Now m of xy is dou z by dou x at y, and n of xy is dou z by dou y at x. So when I differentiate this factor again with respect to y and x, look here. For example, m is dou z by dou x. So I differentiate the m by dou y again. So what happens? Dou m by dou y at x equal to dou square z by dou y by dou x. Is that right? Dou square z dou y dou x. Similarly, n, it is z already differentiated with respect to y. Now I differentiate with respect to x. So I get dou square z dou x dou y. So these two factors are equal. So I can write dou m dou y x equal to dou n dou x y. This is called the Euler reciprocity. So for a state function, delta z is zb minus za, or I can write like this. See, if I put integral like this, which means that this is a cyclic process. Cyclic process means a system goes from a state A to state B, and then it comes back to state A. So in a cyclic process, if you integrate dz, that will be equal to 0. This is called an exact differential. For an exact differential, the cyclic integration from one limit to the upper limit and then upper limit to the lower limit, when you come back to the same state, it gives you 0 value. This is called exact differential. Now we are going to do a simple problem by which you can understand what is a cyclic process. See, volume is a function of a temperature and pressure. And we have to prove that for an ideal gas, the dV is an exact differential. I write V is f of T comma P, which is a function of temperature and pressure. When the volume is differentiated, I partially differentiate V with respect to temperature first, and then V with respect to pressure second. So it is dou V by dou T at a constant pressure into dt, and then dou V by dou P at a constant temperature into dP. Look here, V is actually P by T. So PV is equal to RT according to ideal gas equation. So volume is equal to RT by P. When I substitute RT by P in this place, I can get dou V by dou T at a constant pressure is equal to R by P. And again, when I differentiate this volume with respect to pressure, and I'm getting minus RT by P square. So dV is R by P dt minus RT by P square dP in a whole equation what I have written here. So dV is dou V by dou T at a constant pressure into dt, and then dou V by dou P at a constant temperature into dP. When these things are substituted and are written in a single line, you are getting dV is equal to RT by P dt minus RT by P square dP. So what I ultimately getting, again I would like to differentiate with respect to pressure, this part with respect to temperature, as we have done in the case of Euler equation. You do this, dou R by P into dou P at constant pressure, dou, sorry, this should be constant temperature, dou RT by P square by dou T at a constant pressure. On the left hand side, you get minus R by P square. On the right hand side, you are getting minus R by P square. So both these things are equal and they satisfy the Euler reciprocity. As this function is satisfying Euler reciprocity, then the volume change is an exact differential. So the volume change during the expansion of an ideal gas on the application of a temperature or as a function of pressure, the volume change is an exact differential. So in the next problem, I'm going to prove that the work done is an inexact differential, or it is not an exact differential. See, dW, the work done, is equal to P into dV. But you know that volume is a function of temperature and pressure, and dV is an exact differential. This is what we have proved in the earlier problem. And also dV is equal to dou V by dou T at a constant pressure into dt, and dou V by dou P at a constant temperature into dP. And all these things we have seen in the previous problem. But dW is equal to P into dV, which is equal to RdT minus RT by P into dP. So I simplify this. RT by P is again volume because PV is equal to RT. So RdT minus VdP. Now you differentiate this with respect to pressure at a constant temperature, this particular term with respect to temperature at a constant pressure, to show whether the Euler reciprocity is satisfied here. The first part I am getting dou R by dou P at a constant temperature, which is equal to minus dou V by dou T at a constant pressure. See, this particular part is zero because R is a constant. When a constant is differentiated with respect to a variable, you are getting a zero. As this is zero, this particular part should also be zero. But this cannot be true. Why? Because work done, there cannot be a change of volume with the temperature which is zero. So as these two parts are not zero, then the work done is not an exact differential. This is how it is proved. So the volume change, when it is considered as a function of temperature and pressure, volume change is an exact differential, and work done, when it is considered as a function of temperature and pressure, it is an inexact differential because the work done depends upon the path, whereas the volume change depends upon the state of a function. So the volume is a state function, but work done is a path function. Now, I think with this we have completed all the slides. Right.